Oh, thank goodness. Finally, a calculator problem. Question number 8. Californium-248 has a half-life of 333.5 days. How long would it take a sample to decrease in size by 15 degrees? 15 percent. Percent. Gross. Macaroni. I'm going to do this for you in two different ways. One, remember that we can find the rate of decay of a half-life problem by calculating the natural log. Well, that's an H, and it should be an ln. Does it kind of look like an ln now? I'll redo it. That was ugly. The rate is going to be the natural log of 1/2 divided by the half-life, and this half-life is 333.5 days. Crunch that number and then store it as a variable, but it should be roughly negative 0.002. But again, I want you to store that as a variable. So hit the STO button, it's right above the on button, and store that as some maybe alpha A, whatever, but store it as a variable. And then we want to know how long would it take a sample to decrease in size by 15%. So we're using our PERT equation, but remember when we're talking about percents, it's as if the starting quantity, the P, was just 1. So we can just pretend like it's not even there, and we will get that the percent is going to equal E to the power of the rate, which we stored as A, times time. And we don't know what time is, but we do know that we want the percent to be something specific. We want to know how long it takes until it decreases by 15%. Well, if it's decreased by 15%, that means that 85% remains, so I need 0.85. And so now we can solve this by taking the natural log of both sides. Natural log of 0.85 is going to equal our rate, which again I'm calling, oh, that was silly to call it A because of that A, but I'm talking about that A right there. So maybe I'll put little Scooby-Doobies around it, and you'll know what I'm talking about then, maybe. But this is then going to equal A times T, and so to get T by itself, we're going to take the natural log of 0.85 divided by our rate, which for some reason I'm calling an A in a cloud when I could have just called it R, and that equals our time T. So crunch this in your calculator. Natural log, alpha, whatever you stored it as. Just kidding, natural log of 0.85, close your parentheses, divided by alpha of whatever you stored it by. And you should get 78.194. And what are the units? Well, our units are days. But I want to do this another way for you. Remember we came up with another formula. Our second formula involving half-life was A of T equals our principal quantity times 1/2 to the power of, what was it, T, the time, divided by the half-life. So in this problem, we can get the equation. It's going to be the same deal with the percents. We can get the percent equals 1/2 to the power of the half-life, the time divided by the half-life. So let's plug our stuff in. We know that we want the percent to be 0.85 equals 1/2. The time, we don't know, so that's our variable T divided by the half-life, 333.5, which we can rewrite this as the log base of 1/2 of 0.85 equals T over 33.5. So if I take this, hold on, had to move that over. If I take this and multiply it by 333.5, I should get the same answer. But if you're on a TI-83, you can't do this as log base 1/2. So you would have to do 333.5 times log of 0.85 divided by log of 1/2. And then that should give you your T. And so you should verify that this also works. 333.5 times the log of 0.85, close your parentheses, divided by the log of 0.5, close your parentheses, close your other parentheses, and that equals, again, 78.194. Sweet. But let's do problem number B. Problem number B says, how much of a 90-gram sample would remain after 4 years? And here's the kicker, years, but our rate and all this work we've done is in terms of days. So we need to convert the years to days first. And look, I've given you 365.242 days in the year. That's what Google told me. So multiply 4 years by 365.242 days per year, and you should get a number that I probably should have calculated ahead of time, but I didn't. But anyways, that number is 1460.968. And so that's going to be our unit of time, the days. And so how much of a 90-gram sample remain? Well, I'm going to use our other formula, the A of t, the one with the base of 1/2, because then I don't need to find my rate. I mean, I already found it, but I'm doing this anyways. So A of t equals our starting size, which is 90, times 1/2 to the power of the time, which is 1460.968, divided by the half-life, which is 333.5, and crunch that. And I got 4.320 grams, and there are some decimals, but they're negligible at this point. So again, to do it the other way, we could use the PERT equation. Say that A of t is equal to our principal, which is 90, times e to the power of our rate, which we were calling a earlier, but it's our rate, whatever it is. But no, we were doing a in a cloud, so let's keep doing that, times time, which is again 1460.968. Crunch that, you should get the same exact number.